Welcome to today's lecture on the basics of synchrotron emission. Synchrotron emission is relativistic cyclotron emission. It's what happens when an electron, over here, moving at relativistic velocities, encounters a magnetic field labeled B here. The force on that electron from the magnetic field forces it to move in a tight spiral here, and that acceleration of the electric charge causes photons to be radiated off. And that radiation normally would be cyclotron emission. But as the speed of that electron approaches the speed of light, there's some modifications of that cyclotron emission, some relativistic effects that make synchrotron emission slightly different. So let's begin with the characteristic frequency of cyclotron emission. So I'm going to do just the cyclotron emission here for speeds that are much less than the speed of light. So I'll draw a picture of what this cyclotron interaction looks like from the bottom of this figure on the left. I'll have a bunch of B fields, this time pointing down into the page, so we just see the backs of the arrows of the magnetic field lines. And we'll have an electron here moving with velocity in this direction. And let's just calculate what the force on that electron would be. Well, the magnetic force is equal to minus the electric charge, E, times the velocity in units of the speed of light, crossed with the magnetic field. So to make my life easier, I'm going to label this vector here just the perpendicular component of the velocity. And if we're only considering the perpendicular component of the velocity, then this force just turns into minus E times whatever that magnitude is, times the magnitude of the B field, which we've assumed here is in the direction perpendicular to the velocity. Therefore, we get the full magnitude of the B field over C. We're going to produce this force, which is going to point in this direction, down. And the net effect of this is going to be to curve this electron's path down in this direction. And once the electron is over here, with a velocity moving down, crossing into the B field, the force is again going to be pointing perpendicular to its direction. And as we follow that around, we will force circular motion onto this electron as it goes through this B field. Now for circular motion, the acceleration required to maintain that circular motion is equal to v squared over r. So for whatever radius of curvature of the circle that this electron moves in, v squared over r times the mass of that is the force that's required to maintain the electron in that circle. So using these equations, I can solve for what r is, and I get that r is equal to mvc over eb, where I've dropped the negative sign here because we were just considering the magnitudes. So then we can ask, how long does it take the electron to go around a circle of this orbit, which we can relate to an angular frequency, omega, which is equal to v over r. And when I compute this, you'll see that the v's actually cancel out, and I'm left with the angular frequency being the charge of the electron times the magnitude of the magnetic field over the mass of the electron times the speed of light. And this is the characteristic frequency of cyclotron emission. You'll notice it doesn't care about how fast the electron was moving. It only cares about the magnitude of the magnetic field, the mass of the particle in it, and fundamental constants like the charge and the speed of light. The next thing we want to consider is, where does this emission, the cyclotron emission with this characteristic angular frequency, where does it get emitted toward? If we look at our electron here, at the moment that we see it just at the top of the circle here, being accelerated downward, we know that the expression for Larmor radiation says that power is equal to 2/3 E squared A squared over C cubed. Now, implicit in this Larmor formula for the power radiated is the dependence of power on the acceleration. The power radiated in any particular direction is actually proportional to the projected acceleration seen from that direction. For example, if I had an electron here being accelerated in this direction, and I viewed that electron from the same direction as that acceleration is pointed, as I look at it, I don't see any projection of that acceleration. I'm looking straight down the barrel of it, and I actually don't see any radiation from that charge. Another way of saying this is that the field lines from this charge here don't have any discontinuities when viewed from this direction. But if I were looking down from somewhere different from this direction, I would see a component of the acceleration perpendicular to my line of sight. For a viewing angle theta with respect to the acceleration, I see a projection of the acceleration a times the sine of theta. And the result is that we see radiation being beamed off in the direction perpendicular to the acceleration with a sine squared theta dependence. So in the case of our electron here orbiting in a magnetic field, the acceleration is towards the center of the circle, and therefore the cyclotron emission is radiated both forward and backward with what would look like in 3 dimensions as a torus. So that's plain old cyclotron emission. Now let's start considering the relativistic case for synchrotron emission. And first we're going to deal with just the angular dependence of the radiation that comes off of this electron due to its acceleration. So we're doing the angular power pattern. There are 2 relativistic effects that affect our angular power pattern. The first is length contraction. We're sitting here in the lab frame, where you could consider a spatial grid of x in the lab frame and y in the lab frame. But in the electron's rest frame, the lab frame looks contracted along the direction of motion. So if we take that direction of motion to be in the x direction, the electron sees these gradations along the x direction closer together. So if our electron is sitting right here, being accelerated in this direction, with a velocity pointing in this direction, it thinks it's emitting according to the cyclotron pattern with just the sine squared theta dependence. Under this Lorentz transformation, x in the lab frame is equal to gamma times x in the electron's frame plus the speed of the electron with respect to the lab frame. And gamma, if you remember, is the Lorentz factor 1 over the square root of 1 minus b squared over c squared. And for highly relativistic effects, gamma is generally much larger than 1. So in the lab frame, the electron is here. We see it moving in this direction, but 2 things happen. One is that because of the stretching effect, this length contraction along the direction of motion, the forward-going beam points more forward. It's narrower than just sine squared theta because the whole power pattern has been stretched to the right. And that means that your opening angle, which used to be theta and was approximately 90 degrees in the electron's frame, has been narrowed so that most of the radiation is beamed out to an angle that's about 1 over gamma. And if you want, you can work out in detail exactly what this angle is by noting that the tangent of that angle is equal to y over x in your lab frame. And you can relate that to the y over x in the electron's frame, noting that there has to be a factor of gamma in there. So that was one effect, and that's just the length contraction associated with this gamma. The second effect is that because of the relative motion of the electron with respect to the lab frame, a photon moving perfectly in the y direction in the electron's frame, that photon has to be aligned to some degree with the motion of the electron in the lab's frame. And that means that the backgoing lobe of the synchrotron emission is a bit distorted. The forward-going lobe is tightened to a 1 over gamma opening angle. The backgoing lobe is spread out over a larger angular direction because of the motion of the 2 frames with respect to each other. Now we could work out what that shape of the backgoing lobe is in detail, but it turns out we really needn't bother because of the second effect that comes in from the relativistic motion of this electron, which is just plain old Doppler shifting. Because of Doppler shifting, the frequency we observe in the positive x direction, the way we've drawn it here, is blue shifted with respect to what the emission would have been in the electron's rest frame. This means that the frequency observed in the positive x direction, the direction that in the lab frame corresponds to the direction of motion of the electron, is equal to the frequency that would be emitted in the electron's instantaneous rest frame times 1 over 1 minus beta where beta is just defined to be v over c. Now I'm not going to put in the time dilation effect for this Doppler shift, because pretty soon what I'm going to put in for this rest frequency is the cyclotron frequency, which was already defined in the lab frame. What we're really accounting for here in this Doppler shift factor is just the fact that as an electron is emitting radiation in the direction that it's moving, it's eating up some of that distance as it's emitting. So we'll just use the 1 over 1 minus beta factor here, relating to the frequency in the positive direction. And of course, we have the reverse of that for emission in the negative x direction, where the observed frequency in the negative x direction is going to be the rest frequency times 1 minus beta. Now just to relate these betas back to these gammas, you'll notice that gamma here is just 1 over the square root of 1 minus beta squared, which means that beta squared is equal to 1 minus 1 over gamma squared. So from this you can see that the quantity 1 minus beta is equal to of 1 minus 1 over gamma squared, and if gamma is much greater than 1, we can approximate this, just Taylor expanding this quantity, as 1 over 2 gamma squared. So the upshot of all of this is, if this is our electron here, the forward-going lobe receives a gamma squared boost to its rest frequency, which means in terms of energy, it gets a gamma squared boost in energy. So if we're drawing the power radiated off as a function of angle, this makes the forward-going lobe carry even more power. Whereas the back-going lobe, which was already diffused out due to the electron's motion with respect to the lab frame, is also receiving less energy by a factor of 1 over gamma squared. So this is a red-shifted lobe back here that just matters less. So for all intents and purposes, for synchrotron emission, we can consider only the forward-going lobe. It's the one with the most energy. And remember, this forward-going lobe had an opening angle of about 1 over gamma in each direction. So the total width of this is about 2 over gamma. So the combination of these two effects, length contraction and Doppler shifting, is what's known as relativistic beaming. And it's not unique to synchrotron emission. The effect of relativistic beaming says that most of the energy is going to be directed in the direction of the motion of the charge, with an opening angle that's roughly 1 over gamma. And you needn't consider the back-going lobe at all because it's been Doppler shifted so much that you're getting almost no energy there. All right, so understanding relativistic beaming, we can revisit the question of what is the characteristic frequency, and we're going to adapt it for synchrotron emission. So I'll write down that equation for the cyclotron angular frequency here, EB over MC. Now remember, this was the angular frequency of the orbit of the electron in the magnetic field. So here was our magnetic field. Our electron is moving in this direction. And for non-relativistic speeds, this was measuring how long it took to go all the way around in a circle. But if we were watching the discontinuities in the electric field coming off from this electron, we would also see, again for non-relativistic motion, that the variations in the electric field coming off from this charge would also have that same angular frequency. That this time period of oscillation here would be 2 pi over omega. So for cyclotron emission, the angular frequency of the orbit is the same as the frequency of the photon that gets created. But this is not necessarily the case for what's going to happen with synchrotron emission. For synchrotron emission, we have a similar picture here. We have our magnetic field. And the electron is going to go around in a circle here. But if we're observing from over here this electron moving around, we only observe the electron for part of the time. This is because the emission from this electron is relativistically beamed. So you can almost think of this as a lighthouse. The lighthouse has a thin beam of emission, and we only see that lighthouse for part of the rotation because we can see it here as it's just cresting our little circle here, and the bottom part of its beam is barely pointing in our direction. And we'll see it from then until it crests over this circle. And that means the emission that we're going to get is going to be compressed in time. We'll get it for part of it, and then we basically don't get any emission, or very little, for a period of time here while it's pointed away until we get another blip of emission here. And while for the cyclotron emission, the Fourier transform of that waveform corresponds to one particular frequency, that is a photon of a single frequency, we can see that the Fourier transform of this modulation pattern for synchrotron emission is not going to be monochromatic. It may have a characteristic frequency, but it's certainly not a delta function, because this does not look like a sine wave. So if we want to figure out where the peak of this emission is, we need to figure out a few things. We need to figure out what the width of one of these blips is. This is the time during which our lighthouse beam is on for us, the observer. We also need to figure out what is the time between blips. So let's start with that second question, this time between blips, which I'll call 2 pi over omega rotation. So this is related to the angular frequency of the motion, even though it's not emitting to us that entire time. Now I'm not going to repeat the entire derivation of our cyclotron frequency here, but I will remind you that our force from a magnetic field is equal to, as before, charge of our electron, which is minus e, our velocity over c cross our B field. And just for completeness, I'll go ahead and throw in the electric force here, which was negative e times the E field. In the lab frame, this is 0. In the electron's frame, the magnetic field that we see in the lab frame, Lorentz transforms into an electric field. So in the electron's instantaneous rest frame, it knows that it's being accelerated because it feels the B field as an electric field acting on the charge of the electron. Anyway, we know in relativity that momentum undergoes a Lorentz transformation along with energy. And if we wanted to relate that to a velocity, the momentum is equal to gamma times the rest mass times the velocity. Which means in our previous derivation, where we had called this term over here ma, which was m change in velocity with respect to time, that was our classical expression for the change in momentum with respect to time. But including relativistic effects, this is actually gamma m dv over dt. So really the only flaw in our previous cyclotron derivation was that instead of using m, we should have used gamma times m, which means that the expression for our rotational angular frequency should just be the cyclotron frequency over gamma. So now we know how long we have to wait between blips here. And it turns out, including relativistic effects, that that period is longer than you might have expected because your momentum picks up a factor of gamma. Alright, so now we know how long it takes to go around this circle. But for what fraction of that are we actually emitting? The answer here is pretty straightforward. The angle on this side of perpendicular is about 1 over gamma, because that's the width of the beam coming from your electron. And the width after you're pointing straight at the observer over here is also about 1 over gamma. So the time interval delta t over which the electron was emitting in a way that would get to the observer, delta t emit, was of order 1 over omega rotation, 2 over gamma. And I'm ignoring factors of like 2 pi right now. But as we've said before, just because that's the time interval that you were emitting over doesn't mean that's the time interval over which the observer will see that emission arrive. For example, if an electron started emitting over here and finished emitting here, during that time it was moving along that distance. So a photon that it started emitting from the very first moment that its beam contacts the observer may have only gotten to about here by the time that this electron, which is itself almost moving the speed of light, emits a new photon right here. So the time interval over which it's observed to arrive is much shorter because the electron itself has eaten up some of the distance that the photon needed to fly to get to the observer. So I'll pick a blue color here for Doppler shifting to say that the delta t over which the photons arrive at the observer is approximately 1 minus beta times the time interval over which it was emitted, where 1 minus beta is just the fraction of the space here that was not eaten up by the velocity of the electron. And remember above we said that 1 minus beta is approximately 1 over 2 gamma squared. For large gammas is approximately 2 delta t emit over gamma squared. So if we do the algebra here, what we're going to have is the expression for the width of this pulse. It's the time interval over which the observer will see a pulse of emission from this electron moving relativistically in a magnetic field. And I'll go ahead and put that back as an expression for the angular frequency of synchrotron emission, and we worked out that this was effectively the angular frequency of cyclotron emission divided by a gamma that had to do with the fact that momentum carried a gamma. But then the time interval over which it was emitted had a factor of 2 over gamma, which means that in frequency, which is inverse to time, we pick up a factor of gamma over 2, which comes from the fact that we just see the electron emitting for a short fraction of its total rotation time due to relativistic beaming. And then finally, we have the fact that Doppler shifting compresses the waveform, giving us a shorter time interval for the arrival of those photons than the time interval over which they were emitted. And that's a factor of gamma squared over 2 here. So just to label where these gammas came from, this one was from momentum, this one was from beaming, and this one was from Doppler. So putting it all together, I'm going to drop factors of 2. We have that our synchrotron emission characteristic frequency is of order gamma squared times our cyclotron frequency. And it turns out if you want to be a little more detailed about this, more detailed than we're going to be here, you can work out that there's a 3/2 in front of this, and there's also a sine alpha after this, where alpha is the angle velocity with respect to the B field. Up to this point, the velocity we'd been considering here, here, and here were just the components that were perpendicular to the B field. But our gamma factors, which showed up here, here, and here, cared about the total velocity. So we'll keep our gammas as considering the total component of our velocity, the total magnitude of our velocity here, and we'll incorporate this sine alpha term here to consider just the component of the velocity that's perpendicular to the B field. So when V is perpendicular to B, alpha is pi over 2, sine of alpha is 1, and we get that synchrotron just is 3/2 gamma squared omega cyclotron. But if you have an inclination angle with respect to the B field, omega synchrotron might be smaller. So this synchrotron characteristic frequency is actually the frequency at which synchrotron emission peaks right here. But that doesn't mean that it's the only frequency present in synchrotron emission for exactly the reasons that we described, that this waveform here is not a sinusoid. And in fact, it has a fair bit at frequencies lower than that, so we won't derive this, but it can be derived just by taking the Fourier transform of this waveform, that power as a function of frequency scales as frequency to the 1/3 for frequencies below the synchrotron characteristic frequency, and it falls exponentially for frequencies above that characteristic frequency. And the very last thing I wanted to say about the basics of synchrotron emission is the question of how is it polarized. So normal cyclotron emission, and let's suppose it's going around in a circle, and we're viewing that circle kind of edge on here, like this, with our B field pointing down here. Observed from the top, we see an acceleration that's cycling circularly, meaning that we would see electric fields running in spirals if viewed from the top. And similarly, viewed from below, we'd see that electric field doing the same winding pattern, just with the opposite handedness going down. So the electric field tracing out this winding pattern is an indication that we have a circular polarization when viewed from the top or the bottom, but when viewed from the side, especially if you're completely edge on, you would see a linear polarization if you were looking at it from over here. So this is normal cyclotron emission. It's circularly polarized, in fact, left-handed circularly polarized when viewed from the top, and it's right-handed circularly polarized viewed from the bottom, and it's linearly polarized when viewed edge on. Now we know that most of the emission of the electron is going to happen perpendicular to its acceleration, which is along the line of the velocity here. So we will see most of it probably linearly polarized, since that's most of the direction that you're emitting from. But there is this sine theta dependence, which means that some component of it will be circularly polarized, both left and right. This was the cyclotron case. In the synchrotron case, recall that we have this relativistic beaming effect, which means that even emission that looked like it was being emitted in the y direction in the electron's rest frame is actually beamed to be both in the x and y directions in the lab frame, which means that our circular polarization that we may have originally observed going in the y direction here, we actually get over here at the top of the beam from our relativistic beam. So if this right here is our electron with its relativistic beam over here, the top edge of that is going to be left-handed circularly polarized. Edge on, that beam will see linear polarization, and along the bottom edge of that relativistic beam, we're going to see our right-handed circularly polarized emission. So even though we may be viewing this electron nearly edge on with respect to the magnetic field that would be oriented in this direction, we will see left-handed and right-handed circularly polarized emission along with some linear polarization along the axis. Now if there were just one electron here, that's what you'd see. You'd see left-handed and right-handed. But in almost all situations where synchrotron emission is happening, we actually have lots of electrons spinning around here. And if all of these electrons are spinning around here, their beams and their emission end up overlapping. So one electron's beam may end up here, the next electron's beam ends up over here, next one over here. They're emitting from all different regions next to each other, oriented along the field line of this magnetic field, which means that the left-handed circularly polarized portion of one beam overlaps with the right-handed circular polarization of the electron right next to it. So at almost all points here, you're actually getting a combination of both left and right circular polarization laid right on top of each other by these multiple electrons spiraling around. And left-handed plus right-handed circular polarization is linear polarization. A linearly polarized signal is just a sum of a left circular polarized signal and a right circular polarized signal. So in fact, in an ensemble of a lot of electrons, synchrotron emission is really only linearly polarized. You really see no circular polarization. So the polarization is linear. And you'll see it oriented orthogonal to the direction of the magnetic field. So that covers the basics of synchrotron emission. We talked about relativistic beaming, we talked about the characteristic frequency, we talked about polarization for synchrotron emission. Thanks for listening.